Hey guys, so this is 12.2, day 2. We're going to continue finding limits algebraically like we did last time. Last time what we started doing is finding limits by direct substitution, right? And we sort of started talking about the fact that when you've got a fraction, there is always that possibility that you might get a zero in the denominator, and we all know all is fine and well until you divide by zero, right? So we're going to explore that a little bit more. Now there is actually a particular case called indeterminate form, and what that refers to is when you do direct substitution. And with direct substitution, you get 0 divided by 0. So you have a rational expression or a rational function. You plug the value, x approaches a certain number. You plug that number into the numerator, you get 0. Denominator, you get 0. So you have 0 over 0. Now that's important. We're not talking about 5 over 0 or negative 3 over 0. It's that specific case where you have 0 over 0. That situation is said to be an indeterminate form. The reason is 5 divided by 0, right? That we know will lead to infinity, right? If you have a number divided by a very small number, that's infinity. However, what's 0 over 0? Is that 1? It's not 1. Is it infinity? It's not infinity either. So the thing is, 0 over 0 can actually turn into a couple of things. It can turn into infinity, it can turn into DNE, or it can turn into a finite value such as 3, negative 3, 5, and so on. So when you get 0 over 0, that actually says nothing about the function. You cannot determine anything from the function when you get 0 over 0, hence the term indeterminate form, right? In this case, it is necessary to use other methods to determine the limits, right? So once you get 0 over 0, you're like, we don't know what situation this is, so you have to do something else to hone in on what exactly the limit of that function is. When you get 0 over 0, it's possible that the limit exists, and the terminology for that is it converges, or we say it diverges into negative infinity or positive infinity. So we can either get a finite number, we can get positive infinity, we can get negative infinity, we could also get DNE. All right, let's just do one here. This is the first case here. We're going to find the limit as x approaches negative 2 of this function. So when we substitute x equals negative 2 into the numerator, you get 0. And in the denominator, negative 2 plus 2 is 0. So this is indeterminate form. That means we have no idea what to do. So there are a couple of different ways that we can go about solving this issue. One is by factoring. And if you have a case like this where you have a polynomial divided by another polynomial, that's probably going to be your best situation. So this is going to be equal to. Now, when I'm going to do something to this equation algebraically, right? I'm not substituting in the negative 2. I'm still going to work on the function. I have to continue writing the limit as x approaches negative 2, right? So now this is going to be the limit as x approaches 2, and now I need to factor this. How do we factor a cubic function with 4 terms? We factor by grouping. Well, from the left here, I'm going to factor out an x squared, x minus 3, from the right, minus 4, x minus 3, all over x plus 2. Now I can pull out the x minus 3. So now this is going to be the limit as x approaches negative 2, x minus 3 times x squared minus 4 over x plus 2. And now you know that we can factor that some more. So it's the limit as x approaches negative 2, x minus 3, x minus 2, x plus 2 over x plus 2. Now what happens? This is the best part of all. I can cancel out the x plus 2 and the x plus 2. And what happens? That denominator, which was the reason why we got 0 in the denominator, all of a sudden disappeared, right? So now, right, what do I have left? I'm just going to write that over. This is the limit as x approaches negative 2 of x minus 3, x minus 2. Now, as long as I have not yet started to substitute negative 2 into the equation, I have to keep writing limit, 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 limit. And now you're asking, well, what happens if I don't? And it's very, very simply, you lose points every single time. All right? Now that there is no more simplifying I could do, there is no more combining like terms and so on and so forth, I am now ready to substitute negative 2 into here and here. And now at this point, when I put in the negative 2, I drop the limit. So this becomes negative 2 minus 3, negative 5, negative 2 minus 2, negative 4. Right? No limit here because I've substituted my negative 2. And that finally turns into 20. So do you see that? Initially we got 0 over 0. And you could have said, oh my God, that's infinity. No, it's not. 0 over 0. Oh, that's equal to 1. No, it's not. Right? It was indeterminate. We had no idea what it was going to turn into until finally it turned into 20. All right. Let's do another one. So when you plug in 6 here, let's actually try it out, right? When you plug in 6, you get 36. And now, since I'm plugging in the 6, I don't put limit anymore. Minus 42 plus 6 all over 3 times 36 minus 66 minus 42. Well, that's 0 over 0. So we have to go and simplify this function, right? No limits here. If you do put a limit here, that's actually wrong. So be careful. You can't just play it on the safe side and just put limit everywhere. No. Okay, I'm going to factor the numerator here. And I'm going to get x minus 6, x minus 1 divided by 3x plus 7, x minus 6, sorry. Right? Now what happens? X minus 6 goes away, which looks pretty promising. So this is the limit as x approaches 6, x minus 1, 3x plus 7. Let's plug in the 6, so we drop the limit. 6 minus 1 on top, 3 times 6 plus 7 in the denominator, and that gives me 1 over 5. Okay, a few things to note here. First of all, look at the form here, right? Look at how easy it is to very, very clearly follow my steps here. I have not left anything up to anybody's imagination. Anybody who is reading this, whether they understand math or not, they know that my first step in the first problem was this, then I moved on to this, then I moved on to this. Every single step is divided from the other one, separated from the next one and the previous one by an equal sign. All of these things must be present in your homework, and they must be present on your test when you submit your written work in order to get full credit. If we are calculus bound, then we must be in the correct habit of how to write down work. Okay, let's move on. So that was one way to solve the indeterminate form problem. Another solution to the indeterminate form scenario is rationalizing, right? And when do we rationalize? We rationalize when we've got a situation with square roots. Okay, so take a look at this problem. I have the limit as x approaches 25 of x minus 25 root x minus 5. Okay, so when I plug in 25 into the numerator, 25 minus 25 is 0. Root 25 is 5 minus 5, 0. I get 0 over 0. This is indeterminate. Now, what am I going to do here? Do you remember back in the day you learned about conjugates, right? When it was with complex numbers and we had 3 plus 2i, its conjugate was 3 minus 2i. In the case of roots, the conjugate, if I have root x plus 3, is root x minus 3. Similarly, if I have, let's say, 2 minus root x, the conjugate is 2 plus root x. All right, so here what we're going to do, we're going to identify where the root is, and we're going to multiply that term with its conjugate. So here I have root x minus 5. I multiply by root x plus 5. But I can't just do that to the denominator and not to the numerator, so I multiply the numerator as well. Notice I instinctively placed parentheses around everything. That's proper form. That's sophisticated, dignified math student form. All right, so we're still not plugging in x equals 25, so we have to continue with writing the limit. Now in the numerator, I have x minus 25, and I have root x plus 5. I know every fiber in your body wants to distribute that and multiply that. Resist that urge, because look at what's going to happen. Something beautiful is going to happen now. Let's multiply the denominator. This is a minus ba plus b. So I square the first part, I get x. I square the second number, I get 25, with a minus in the middle. Oh my God, what happened? Where else have I seen x minus 25? Right here, guys. Isn't that fantastic? Tell me that's not a miracle right there, right? That's a miracle. So now that goes away, what do I have left? The limit of x approaches 25 of root x plus 5. Now that there is no more simplifying I could do, there is no more algebra I could do, plug in the 25, and once I plug in the 25, I drop the limit, and I get a value of 10. Now you're probably asking, okay, you probably got lucky on that one. They canceled out. Is that going to happen every single time? Every single time. The only time that won't happen is if we've made a mistake somewhere. So let's just try it out with this one. X approaches 0. The limit as x approaches 0 of this function. When I plug in 0, I'm going to get 2 minus the square root of 0 plus 4. That's 2 minus 2, 0, divided by 0. Okay, that's 0. So this is indeterminate form. That means I need to simplify this. Because I have a root situation happening, I need to multiply by the by the conjugate. Well, here it's going to be 2 plus root x plus 4, right? So this time it's in the numerator. It's okay. You just multiply whatever term it is. And then you have to do the same thing to the other part. Okay. This is the limit as x approaches 0. Okay, you have to multiply in the part where you have the conjugate. Like in this case, it's the numerator. a minus b, a plus b. I square the first term, I get 4, minus I square the second term, and I get x plus 4. And because I'm a sophisticated math student, I put that in parentheses. In the denominator, again, you've got that urge to distribute the x. Don't. Just copy it over. All right. So this is the limit as x approaches 0 of, let's distribute that negative, 4 minus x minus 4 over x, 2 plus x plus 4. Limit as x approaches 0. What happens if we forget the limit? Minus 1. Okay, 4 minus 4 cancel out. I have negative x over x times this lovely parenthesis. Okay, x's will cancel out. So what do I have left in the numerator there? Limit as x approaches 0. I have a negative 1, don't forget, over 2 plus root x plus 4. Now, there is no more algebra I could do. I plug in the 0, negative 1 over 2 plus root 4, because it's x plus 4, so that's 0 plus 4. Negative 1 over 2 plus 2, negative 1 over 4. All right? Lovely. All right. Let's move on. Let's move on to limits at infinity. What happens if I have to find the limit of a function as x approaches infinity? So remember, when we have x approaches infinity or negative infinity, what we used to call this before was end behavior. Now, the term end behavior was fine when we were in Algebra 2, but now that we're going into calculus, end behavior is so 2019, right? Now we need limits at infinity. Okay, so this is the end behavior. Let's talk about types of function. Let's talk about even functions and odd functions. So look here to the left, I have an even function. How do I know it's an even function? Because it's symmetric around the y-axis. And if it's an even function, I know that both ends, right, will either go up simultaneously or go down simultaneously. So as I go to positive infinity here, my y value goes to positive infinity. And on the opposite side, as I go to negative infinity, I'm still going to go to positive infinity. Okay, here I have an odd function. And what's the characteristic of an odd function? That one end goes to positive infinity, while the other end will go to negative infinity. Okay? All right, so that's one thing over there. Even and odd functions. And how do I know? How do I know when I look at the power of x, whether it's even or odd? Well, for even functions, this exponent is even. So for example, f of x equals x squared, y equals x to the 4, and so on. For odd functions, you could probably imagine you're going to have an odd exponent. Okay? All right, so that's that. Now, let's talk about a polynomial. What if you have a polynomial, x to the 6 minus x squared plus x cubed, and so on? Right? Well, let's take a look at this first equation in A. I have 4x to the 6 plus 3x to the 5th minus x. And I'm evaluating that as x approaches infinity. Okay, infinity is such a large number. Let's say x equals 1,000,000. Okay, here I have 1,000,000 to the power of 6. A million already has 6 zeros. To the power of 6, that's 36 zeros. Next to it, I have x to the 5. A million, 6 zeros, to the power of 5 has a measly 30 zeros. So think about that. The difference between this first term and this next term is 6 zeros. That means this first term is a million times bigger. And that's only when x approaches, when x was a million. Well, what if x is bigger, a billion, a trillion, and so on? So you see, as x approaches infinity, it's going to be this first term that's the most important, right? We've talked about that before. Do you guys remember when we talked about end behavior? So same sort of situation. When we're talking about x approaches infinity, all we need to look at is the term with the highest power. This goes away, that goes away. Ignore it. So now I ask myself, okay, I have x to the power of 6. That's an even function. Like this one here, even function. It goes in the same direction in both ends. Now, look at this. Is the number in front positive or negative? That's a positive 4. That means this function, the limit of this function as x approaches infinity, is going to be positive infinity, which we say is d(n)e). All right, let's take a look at the next one. X approaches negative infinity this time. Okay, now what's the term with the highest exponent? This one. All right, so this is an x cubed. That means one end is up, one end is down. It's negative x cubed. If it's negative x cubed, it looks this way, right? So that means as x approaches negative infinity, my y value goes to positive infinity, d(n)e). Let's take a look at the next one. What's the term with the highest exponent? This. X to the 5th, it's odd. That means, and it's a positive 4. That means it's up on the right and down on the left. So as x approaches negative infinity, this goes to negative infinity, which is also d(n)e). Let's be consistent and put parentheses. All right, what about this one? Negative x squared. Both ends face down, so whether I'm going to positive or negative infinity, this is negative infinity or d(n)e). And there you have it. I'm at the 23-minute mark. I'm sorry, but I will stop right here and I will see you guys in class. You can now go and do your homework. Make sure you write down all of the questions and every single step for these. For the infinities, the limit as x approaches infinity, there doesn't need to be that much work shown. All right, have fun.